Good day, my friends. So, nuclear physics is not limited by nuclear reactors and all that is connected to nuclear technology, and also it's also a part of elementary particles physics. Cosmic rays is also an important part of modern nuclear physics, and today we will know what is it. So, clicker, please. Clicker was charging. Thank you. And one of the most important elementary particles in cosmic rays and elementary particles for nuclear physics research is muons. What is muons? In fact, it's a part of cosmic rays. Cosmic rays is a flux of elementary particles. Then, elementary particles that, in fact, covers all our surface. And if you look for this room, for example, and look at your body, every second about 100 muons are passing through your body. So that's the thing. Every second about 50 muons are passing through your body. And this is a constant flux that we can face on the surface of our planet. And what is muons in fact? Muons in fact is just well, it looks like electron and it's interact like electron, but it's heavier in 200 times that an electron, and it means that this particle has excellent penetrating ability. From one hand, it gives a perfect response in any kind of detector, and from other hand, it can pass through a very deep places, for example, deep underground. It can go through hundreds of meters of rock, and you even can detect it in the 2 kilometers under the ice. So, how it looks like? In fact, for physics, for theoretical physics, it looks like a process, for example, of decay of pi meson. It can look like that. Or this is a process like this muon decays into electron and couple of neutrino. And how it looks like by the eye. This is an example from bubble chamber, and here you can see like how in accelerator and pi meson it goes like that in magnetic field. It's rounded, and it decays in this small line. This green line is a muon that is decayed to positron and to neutrinos. Neutrinos are invisible to the eye since they don't interact with the detector, and here you can see how it looks like. This is a muon. Welcome. And this is a bunch of muons from accelerator also in such detector. It looks like tracks. So, how to catch muons? So, this is a very common dosimeter that you can buy in some special shop. And the idea is that if you place it on the table, the most hits that it will detect, it will be hits from muons. It's not from beta particles, it's not from alpha particles or gamma. The main radiational flux on our Earth's surface is a flux of cosmic ray muons. And from other hand, for high energy muons, we build huge detectors. And one of them is detector Ice Cube, is placed on the South Pole, so in Antarctica, and this is really a masterpiece. It's situated, just imagine it, South Pole, Amundsen Scott Base, United States holds it. And there at South Pole, there is a detector under 2 kilometers of ice, 2 kilometers. And it has a volume of 1 cubic kilometer. And it's filled with detectors of Cherenkov radiation coming from muons. And also, such detector detects muons. They go from atmosphere and gives response in it. And also, it can detect muons from underground that are produced by neutrinos. So this is, for comparison, an Eiffel Tower. And this is a South Pole. Just imagine how hard to get there. And this is a very typical detector for detection of atmospheric muons. It's called muon hodoscope. So you know what is telescope. Telescope is a device that detects radiation from some direction. Also, you can build multiple telescope or multi-directional telescope that can detect particles from several directions. And muon hodoscope is a detector that can detect all flux of muons from all directions and know from which direction each part came. How to use such detectors? You can make tomography or muonography using this flux. And this is a very bright example. So this is a water tower. And this water tower can be full or empty. And if you place such detector nearby and measure muon flux, you can see the difference in muon flux when it's full. When it's full, there is more matter, water. It stops muons, and it will decrease the number of muons. This is an example. Another example, another way how to detect it is to place muon detectors around our target, around the object we try to explore. And in this case is very precise, and this is called muon tomography. This is called muography. And the last way is how we detect features in pyramids. So I will talk it further. So this is a real example. This is placed in MEPhI, and this is a really huge detector so that we hold on experimental complex nevot. Experimental complex nevot itself is a really bright detector that it consists of 2,000 tons of water in MEPhI, and above it we have these 4 muon hodoscopes. It's called uragan. The area of each detector is about 12 square meters. And so each detector can detect about 1,500 muons per second. It's a huge flux. And this is how it works. It detects flux and looks whether it's still or not. And here is an example. So this is a map of Moscow region. And this color correspond to muon flux. If it's green, it means that it's common. That's the same flux that was yesterday. And here you can see change in this color. It means the decreasing number of muons. Muons are generated on the height about 15 or 20 kilometers. And if you see decreasing number, it means that something happens there. And this is an example of a large thunderstorm that was in the region. And in fact, what is the most important, that such thunderstorms can be detected in muons hours earlier than meteorology can detect this. So this is a bright example how we can detect it for weather and to save human lives, because large hurricanes happen in our region rather rarely, but they can kill people. And what is another important thing, that its name uragan translates it's a translation to Russian word hurricane. Another example is how we detect cosmic weather. So what is magnetic thunderstorm? Magnetic thunderstorm comes when from sun we get large coronal mass ejections. Is a huge clouds of plasma, and these huge clouds of plasma can stop cosmic rays from galaxy. And that means if such cloud comes closer to our planet, we can see decreasing number of particles. And this is an example how we can see such coronal mass ejection, this large cloud, as day before magnetic thunderstorm arrives. In fact, with other methods, we can detect it only about 40 minutes before it. So it's a very important instrument. So that was in MEPhI. So also, in other countries, in other regions, tries to use muons in real applied research. And this is volcanology. So this is a way how to find a moment when magma comes through the volcano. And if you place muon detectors from the different parts of rock, different parts of a volcano, you can find the decreasing flux of muons. And if it decreases, it means that something happens, that magma raise up. Another way is custom control. In the custom control, we use two pairs of detectors. One of them is situated above a track, and another pair is situated below it. And all the reflections of muons can be detected by these devices. And here is a response. So in such container, it's with lead bricks, a word is placed, and here is a response of detectors. So you can see that it can find even a word placed with lead bricks that can be detected by muons. What is important, it takes only several minutes to get such a picture. And why it's important also, because it cannot be lead, for example, it can be uranium, plutonium, or something like that. Another important application of muons is the control of atomic power plants. And this is a patient that our laboratory made for such research. And in fact, firstly, it was tried in Los Alamos National Laboratory when they made graphite blocks with uranium inside, and they saw how this uranium is placed inside this prototype of reactor. And the real application was at Fukushima inspection, when you know all this tragedy there, and the problem is that is the position of nuclear fuel after this crash was unknown. Nobody knew whether this fuel is still in the reactor or maybe it's just made its way under the ground. And the muon detectors helped. So they placed detectors at the territory at about 200 meters from this reactor. They measured the flux of muons, and this is the response. So as you can see, there is no any fuel here inside. Not any muon is absorbed there. And this is a real example from our laboratory in MEPhI. So last year we developed special detector that was made specially for muon tomography of Kalininsk power plant. And this is a building of it. And inside this building there is a nuclear reactor, water nuclear reactor inside this. This is how this detector looks like. In fact, it's about 3 meters in height. And this is a response, and you can see the lines of the nuclear building. And here is the place of nuclear reactor. And you can see that the most dense and heavy elements are placed here. Another thing, archaeology. In archaeology, you can use muon detectors to look through great large buildings. And the first try was in 1967. Nobel Prize Luis Alvarez made his experiment in the pyramid of Khufu. So in Russian it's Khefren, the pyramid of Khefren. He placed detectors deep underground below the pyramid, and he tried to check does this flux really correspond to our predictions or not. And he didn't succeed. He found nothing there. Another try was in Central America, in the city of Teotihuacan, and below this pyramid also was placed a large detector of muons. And he tried to, look for the muon flux in these angles, in these zenith angles. And this detector also found nothing. But occasionally the luck was leading by Japanese scientists, and they placed very small and simple muon detectors in the Queen's chamber below pyramid of Cheops. And the idea is that these detectors just placed without electricity and nothing about a year there, and they detected the full flux for years. It was a large statistics, and they found anomaly, and this is how it looks like in data. So the black line is expectation from simulation, and the red dots, it's real experimental data. And here you can see a huge excess, and that means that at one region of the pyramid there is a real void. And what is this? French physicists placed additional detectors, and they could find a special place that is situated above large gallery. So maybe if you were there, so you remember this huge gallery that you are going up to the stairs for a long time, and above this gallery there is another place, another void that is by the size is the same like it. So you can imagine how large is it. Another try was made last year, and they placed such detectors not in the Queen's room, but in the point of G here, and they found that also some additional room is below this place. And what is the funny thing that people from scientists that explore pyramids, that Egyptology is called, they have a lot of doubts about that. So what is the idea? Is that, I don't know, do you know why this chunk of Cheops has additional places above? There is the idea that pressure of blocks can destroy this room, and to prevent it, there is made special technical rooms above, and especially with these special blocks with the form of triangle, and this prevents this block from any crash. And in Egyptology, they say that additional for the main gallery, they think that there is also special place above with such a room, and it should be just to prevent this main gallery to be, well, to prevent it from high pressure of the rest of the pyramid. And another experiment was made in Pskov-Pechersky monastery. This research was also several years ago, and it really gave a bright result in joint operation of MEPhI University and MEPhI. And it helped to find new rooms in the combs of Pskov-Pechersky monastery. This is how these detectors of muons looks like. And this is 3D geometry of combs below this monastery. And this green points is the unexplored rooms under this monastery, and this was found only because of these muon detectors. And finally, this is also the very last scientific results. In Canada, a physicist that was looking for years for caves, and they were looking for heavy elements, and they made this special detector. This is also a muon detector, and they place it into this long how it's called, so holes, yes, okay, these long holes, and they say that such single hole can detect with these detectors can detect uranium deposits in the distance of about 500 meters, or even if you are lucky, 1.5 kilometers. And that means that it will help to find uranium deposits and save billions of dollars for drilling of such holes. So in conclusion, when I guess 100 years ago but Victor Guess found cosmic rays, he never knew that it can be used in some applied research like electricity and something like that, or maybe neutrino. So we don't even know where our research will give its application. And muons is just a bright example of it. In fact, it covers maybe the most part of human work and life, and you can find its application everywhere, from pyramids to weather, to cosmic weather, and even to some growth of the food. So, if you like it, come to MEPhI, look our muon detectors, and maybe you will be the one who made the new application of these bright particles. Thank you.
Thank you, Egor. Now it's time for questions. Who will start? Yes.
Здравствуйте. Скажите, Каким образом устроен детектор и как проходит вообще механизм детектирования мюонов?
Okay. It's from the beginning, so we can. Yes. Okay. So the main types of detectors are scintillator detectors or gaseous detectors. So these are two types of detectors that are usually used for detection of muons. Also, we can use Cherenkov detectors, but it's a very large one. Okay, so what is dosimeter? It's a device that contains Geiger tube. So what is Geiger tube? It's just a cylinder with a wire inside, and in this wire you give a high voltage. It's about, well, maybe 500 volts per one tube. And this tube is filled with special gas. It's usually argon with CO2 and usually some alcohol there. And when a particle hits this tube, it ionizes the gas. When free electrons go to the electric field, it gets high energy and it produces, well, a small lightning inside. And this lightning gives an electric signal that you can detect with common types of electronics. So the idea, a particle comes, it brings, well, it makes a small lightning inside and you can detect it. Another way is to use scintillator detectors. Scintillator detector is some material that makes, when a particles go through it, it gives a flash of light inside. And for example, analogs of this muon horoscope consist of huge number of small scintillator parts, and when a particle hits it, there is a flash of light, and you can detect this flash of light with a photomultiplier or something like that. And when you know the points at which this flash of light was seen, you can place experimental points, and then with the methods of least squares, just make a line and calculate the direction of a particle, if it's clear.
Thank you. Next question.